Hello everyone, welcome back. In this video, we are going to learn multi-threading best practices in Java. Subscribe to the channel to keep learning and growing your Java skills. So let's get started. So imagine your multi-threaded application works perfectly during development. You test it again and again, everything looks correct. Okay. So you tested like 100 tests, 1000 tests. Okay. Then you deployed it to production, and suddenly once in a while the data is wrong, and sometimes the application becomes stuck, it hangs. Sometimes performance get worse. Okay, performance will drop. And the strangest part is when you try to debug the problem, it disappears. Why? Because multi-threading bugs often depend on timing. A tiny change in thread scheduling can completely change what happens. So knowing how to create threads is not enough. The real skill is knowing how to design concurrent code that avoids problems in the first place. Okay, so in this video we will cover 5 multi-threading best practices that can help you write safer, simpler, and more maintainable concurrent Java applications. And the first tool can eliminate many concurrency problems before you even need synchronization. Okay, so let's see. So first one is avoid unnecessary shared state. Okay, so this is first best practice in which avoid unnecessary shared mutable state. So many multi-threading problems begin with multiple threads can read and modify the same data. Okay, so once data is shared and mutable, we need to think about synchronization, okay, visibility, atomicity, race conditions, and locking those things. So before asking how should I synchronize the variable, so ask a better question. Does this variable actually need to be shared? If each thread can work with independent data, many concurrency problems disappear automatically. Okay, so we should understand the shared and independent state. So compare these two designs. Okay, so in the first design, 3 threads modifying the same shared state. Okay, here. So 3 threads are modifying. Now we need to carefully coordinate access. Okay, in the second design, each thread is working primarily with its own independent data. There is less shared mutable state and therefore less need for synchronization. This does not mean shared state is always avoidable. Many applications genuinely need threads to share information. It depends on totally what requirement we have. Okay, but unnecessarily sharing creates unnecessarily complexity. Okay, so a powerful principle in concurrent programming is prefer immutable data and local state where practical, and share mutable state only when the design actually requires it. Okay, so when requirement comes for share mutable state, then only we should use it. Okay, now immutable data. Immutable objects are specifically useful in concurrent programs. An immutable object cannot have its state changed after creation. Okay, let's say if multiple threads only read immutable data. Okay, so we know, right, string is immutable, we cannot change this. If multiple threads only read immutable data, they cannot reuse to modify that object's state, correct? So this removes an entire category of concurrency problem. Immutable means what? We cannot modify the data, and if we cannot modify the data that is immutable, even if multiple threads are utilizing it, there is no race condition or nothing, because we are not manipulating the data. Okay, so there is no concurrency problem. Okay, in this example, you can see string is immutable. Records can also be useful, okay, when designed with immutable components. So immutability alone does not solve every concurrency problem, but reducing mutation and shared mutable state can make concurrent code significantly easier, okay. So it is easier to share safely. Okay, now the second best practice is minimize synchronization. So synchronization is essential when multiple threads need coordinated access to shared mutable data. Okay, so we have a synchronized code and multiple threads wants to use it. In such cases, we will go for the synchronization. But synchronization also means threads may have to wait for locks. If we predict far more code than necessary, okay, we reduce concurrency. Imagine holding a lock while performing a large amount of unrelated works. Okay, so let's say if one thread is holding this lock and it is doing multiple unrelated work, then in that case other threads needs to wait for those amount of time, those period of time. Correct? So other threads needing that same lock are forced to wait, even though much of that work may not require protection. So the goal is not to avoid synchronization when correctness requires it, okay? Goal is to synchronize the right critical section. Okay, we should not synchronize the whole code. Only critical section should be synchronized. Okay, now we will see. So here is a simple example. Suppose only update shared data. Okay, here we have update shared data. Okay, so only update shared data actually requires the lock. If we also perform file reading, calculations, and unrelated operations while holding the same lock, other threads may wait unnecessarily. That is not required. Okay, so instead what we are doing, where correctness allows it, perform independent work outside the synchronized section. Okay, so I mean to say only critical sections should be covered as part of synchronized code. Any other independent work should be kept outside the synchronized section or block. Okay, so then protect only the shared state operation. We should keep the shared state operations in that synchronized block. So this will reduce the amount of time the lock is being held. Okay, but be careful, do not make a critical section smaller. If doing so breaks the atomicity or consistency or operation requires. So the correctness should always come first. Okay, now there is an important difference here. Minimizing synchronization does not mean removing synchronization. Okay, that is required for correctness. Never remove synchronization simply because you think, okay, it might improve performance. Doing that can introduce race conditions, visibility problems, and corrupted state. Okay, so first make the problem correct, then measure performance. Okay, if synchronization is actually a bottleneck, optimize the design carefully. Okay, so the rule should be like, first should be the correctness and second should be the optimization. Okay, now our third best practice is to prefer managed executors and thread pools when dealing with many tasks. Okay, we have seen the concept of thread pools, right? So creating a new thread manually for every task can become expensive and difficult to control. Each thread consumes resources, right? So too many threads can increase memory usage and context switching. So a thread pool allows us to control the number of worker threads and reuse them across multiple tasks. So we have seen, right, in the thread pools concept of we will be having the set of worker threads, and this set of worker threads will be performing n number of tasks. Okay, so we should use the concept of executor service, the thread pool. So instead of managing individual thread creation ourselves, we submit tasks to an executor. Okay. Now, thread pool gives us several advantages. Okay. Worker thread can be reused. Okay. We can limit concurrency instead of creating an uncontrolled number of threads. Task can be queued. Okay. And executors provide lifecycle management operations as shutdown. Okay. So there is a lifecycle management. Okay. But simply using a thread pool does not automatically guarantee good performance. Okay. So the appropriate pool size depend on the workload. So CPU intensive task and input output intensive task can have very different requirements. So always use executors deliberately rather than blindly creating one pool configuration for every problem. So let executors manage these things. Okay. Now one important point. Don't forget to shut down. Okay. So when we create an executor service, we also need to manage its life cycle. Okay. As we learned earlier, worker threads in a typical executor service can keep the JVM alive. We have seen, right? So JVM will be alive until any one user thread is under process. User thread, user or worker thread. Okay. If any one user thread is in active state, the JVM will be alive. And if all user threads are terminated, then JVM will start its shutdown process. So when we are finished submitting tasks, we need an appropriate shutdown strategy. Okay. For simple examples, that may involve calling shutdown. But in real applications, shutdown design may also involve waiting for tasks, handling timeouts, and deciding what to do if tasks do not terminate. So the important point is, if you create an executor, think about how and when it will be shut down. Okay. Now, the fourth best practice is to handle interruption correctly. Okay. So this is an area where many developers make mistakes. Okay. So suppose a thread is sleeping. Okay. Here, suppose a thread is sleeping or waiting and receives an interruption request. Then it will throw what? It will throw interrupted exception. Okay. A common mistake is to catch the exception and simply ignore it. That can cause the thread to lose important information that someone requested it. Okay. To stop waiting or cancel its current work. So interruption is what? It is a cooperative communication mechanism. Interruption is cooperative communication mechanism. So your code should respond to it intentionally. Okay. So if your method can propagate interrupted exception, that may often be cleanest option. Okay. Here, see. Why? Because it allows the caller to decide how to respond. But sometimes you catch interrupted exception inside a method that cannot or should not rethrow it directly. Okay. So in those kind of situation, a common pattern is to restore the thread's interrupt status. How you will restore? Using thread.currentThread.interrupt method. Then your code can stop its work, return, perform cleanup, or otherwise respond like appropriately. Okay. So why restore the interrupt status? Because throwing interrupted exception typically clears the interrupted status. So restoring it preserves the interruption signal for higher level code that may need to observe it. Okay. So as we learned earlier, interrupt is not a 4-skill operation, right? It is not a 4-skill operation, interrupt. It is a like cooperative signal. Okay. Whenever we use interrupt, it does not mean this thing. It means cooperative cancellation. So code performing longer running work may explicitly check its interrupted status. And this is why well-designed concurrent tasks should have a clear interruption and cancellation policy. Okay, if code simply ignores interruption everywhere, shutting down or cancelling task cleanly become much harder. Okay, so this should be taken care. Now, our fifth best practice is to design carefully to avoid deadlocks. We have seen the concept of deadlocks. So we learned that deadlock can occur when threads form a circular dependency, okay, while waiting for locks. So in the example we have seen, if thread 1 is acquiring lock, is holding A, and thread 2 is holding B, and thread 1 is requiring B, but B is currently held by thread 2, and thread 2 wants A, which is currently held by thread 1. So it is a kind of circular dependency. Thread 2 is waiting for thread 1 and thread 1 is waiting for thread 2, and they are waiting forever. So it is a deadlock. None of them can continue. Okay. So deadlock may simply make parts of your application stop making progress. So deadlock prevention should be part of your locking design from the beginning. Okay. And we have seen the consistent lock ordering. We have seen the consistent lock ordering. What was the consistent lock ordering? The order should be same. Okay. If order is reverse, it will be deadlock. Okay. So one of the most important deadlock prevention technique is consistent lock ordering. If multiple threads need the same set of locks. Okay. So establish a global order in which those locks must be acquired. So if you are setting like, okay, first A should be acquired, then B, then every thread should follow that rule. Then only it will work. So it should follow same lock ordering. Otherwise it will be in deadlock state. So consistent lock ordering prevents that particular circular wait pattern from forming. So the simple design rule can prevent many deadlocks. Okay. So there are several other useful practices for reducing deadlock risk. Avoid unnecessary nested lockings. Okay. And be careful about calling unknown or potentially long running operations. Okay. Be careful of these things. And when you use explicit lock API techniques such as try lock may be useful for certain designs. Okay. So based on requirement, use try lock. Okay. So the more complicated your locking graph becomes, the harder your concurrent code is too. Okay. So think what is the requirement, and based on the requirement, just do the analysis, and based on the analysis, go with the proper or appropriate approach. Okay. So let's bring all 5 best practices together. So first was the avoid unnecessary shared mutable state, right? So the less mutable state threads here, the fewer coordination problems you create. Okay. So less sharing is fewer concurrency problems. And second was minimize unnecessary synchronization. So protect only necessary critical section. So only add those kind of data or code in the critical section which are shared. Okay, shared mutable data. Okay. And the third is prefer managed executors and thread pools when working with many tasks. So always prefer thread pools to control and reuse threads. And the fourth is handle interruption correctly. Do not simply catch interrupted exception and silently ignore it. Okay. And the fifth one is design your locking strategy carefully to avoid deadlocks. So these practices all have one goal, that is make concurrent code easier. Okay. So yeah, so here is the most important principle in the entire module. Good multi-threaded code is not the code that uses the large number of threads. It is not the code with the most locks. Okay. And it is not the code that uses the most advanced concurrent APIs. Good concurrent code is code that is simple. Okay. Simple enough and correct under different thread schedules and predictable in its behavior. So concurrency adds complexity. Okay, so every time you introduce another shared variable or say another lock or another thread, ask yourself whether that complexity is actually necessary or not. Okay, so the simplest correct currency design is often the best design. Always focus on simplicity. Your application will be working good and will give a good performance. Okay, now so before shipping your multi-threaded code, ask yourself these questions. Okay, so these questions are: is mutable state shared between the threads? Okay, if yes, how is access coordinated? Okay, are we holding locks longer than necessary? Are task and executor managed properly? What happens if a thread is interrupted? Are explicit locks always released correctly? So we have seen, right, how to release using finally block. And if multiple locks are involved, can their acquisition order create a circular dependency? So these many questions, if you're asking during design and code review, it is much easier than debugging a rare concurrency problem in production level. So we can find the bug before production. Okay, so now we have now covered the major foundations of multi-threading in Java. We started by understanding what threads are and how to create them. Then we explored the thread life cycles and important thread methods. Okay, thread life cycle and thread methods. Then we learned how race condition happens. Okay, race condition happens and how synchronization protects the shared data. And we explored the inter-thread communication using wait, notify, and notify all. And we understood the deadlocks and how careful lock design can prevent the deadlocks. Then we moved into daemon threads, the executor framework, callable and future, and explicit locking with lock and ReentrantLock. And finally, we brought everything together with the best practices that helps us design safer concurrent applications. Okay, but knowing multi-threading concept is one thing, and recognizing concurrency bugs in real code is another thing. So whenever you write multi-threaded code, always remember: reduce unnecessary shared state, synchronize carefully, manage threads at the right abstraction level. Okay, and always respect interruption, don't ignore interruption. Okay, and design your locks before they become a problem. So choose appropriate locking mechanism. And that is how we move from simply created threads to writing reliable concurrent Java applications. So that's all for this video. I hope you now have a clear understanding of multi-threading in Java. Thanks for watching, and I will see you in the next video.